Okay guys, let's take a look at our lesson on geometric series, the nth term test for divergence, and telescoping series. These are the first 3 of the 10 tests that we're going to be looking at in this unit on learning about convergence or divergence of a series. So we're going to start with the one we're most familiar with, and actually we worked on this one last year, the geometric series test. And we're going to start with that one. We're familiar with it. It'll be a nice place to start. Okay, so what it tells us is that if we have a geometric series that's in one of these forms. Now I need to talk about these 2 forms. These are just the typical normal forms. It doesn't mean that if it doesn't look exactly like this, you can't use it. You know, sometimes maybe it'd start at 1, and have an N here. It's okay. It's all right. These are just the 2 normal. These are the typical forms that you would see a geometric series written in. Starting at 0 and having an exponent of n, and starting at 1 and having an exponent of n minus 1. That's just typical. It's not required to use this test. So if the geometric series, so we look at it, and if the series common ratio, the absolute value of the common ratio, is larger than or equal to 1, then what this test tells us is that the series is going to diverge. If our common ratio, the absolute value of it, is less than 1, then this test tells us that our series is going to converge. Also, which is unusual for us, it is typically quite difficult to find the actual sum of a series. Some of them are easier than others, but for geometric, we have a cool little formula that we can use. This formula, perhaps you remember it from last year, tells us, basically it tells us how we can find the sum of the whole series. So that's sometimes you will be asked to find the sum, and we always hope that it's on a geometric one where we can actually use this cool little formula. Remembering that the A is our first term and the R is our common ratio. Alright, so let's look at a couple of these. I have a couple of problems that we're going to work that use the geometric. So it asks us to determine whether the following series converge or diverge. Alright, so in order to find that out, I just need to know what R is. So what I do is I investigate. Now, many of you can probably see this. I'm going to rewrite it so it looks more like a normal geometric series. So I would rewrite it so it looks like this. A little bit easier to recognize. And so from this we can see that our R value is 1/2. And so since our R value is 1/2, we refer to our geometric series test, and we see that that value is less than 1. So this is less than 1. So therefore, these 3 dots are a mathematical symbol for therefore. I mean, you don't have to write that, but when you see me doing that, that's what it is. Therefore, this series converges by the geometric series test. Now, for my students that love to conserve energy, we have to write this out, okay? They don't know what a GST is, okay? They don't know what that is. That's not a normal acronym. You're going to have to write out converges by. We're going to have 10 tests under our belt, okay? 10. And we have to write which one we use. We have to say how we know it converges or diverges. So this converges by the geometric series test. No acronyms, okay? Geometric series test. Just take the extra few seconds and write the words. It'll be fine. All right. So let's take a look at our next one. Now, since it converges, we could actually find the sum. And we would just use this formula. And let's just practice. I mean, they're not asking us, but let's make sure we remember how to do that. Our first term would be where we put whatever this starts at. This particular series starts at 1. I put a 1 inside here, or whichever one, these being the same thing. Put a 1 here for n, and I get 3/2. 1 minus, and we said our r was 1/2. So this turns into 3/2 over 1/2. And what is that? That's 3. So the sum of that series, if you took the time and added all those numbers up to infinity, which we can't, we would get a 3. Okay? So that's that one. All right, let's take a look at this one. It's already set up kind of nicely for us. It's r is 3/2. And we know from that immediately what happens, right? This series is going to diverge. So we would say, therefore, this diverges by the geometric series test. So, remember when we started in working on calculus and we found out about e to the x and we thought, oh, how wonderful that is. Every time we had to integrate or take a derivative of e to the x, we're like, oh, that's so nice. That's how you're going to feel with these guys. Every time you come across a geometric one, you're like, oh, that's great. There's a geometric one. I know exactly how to do that. Because when you have problems, they're all going to be mixed up. I'm not going to tell you which test to use. They're just going to all be jumbled on a piece of paper, and you're going to have to work through and see which test to use. So you're going to have to be able to identify which is which. So when I have to substitute a 1, we can do it on either. Let's go to the original. When I take this, whatever this number is, and substitute a 1 in there, I get 3/2. And so that's my first term. Good question, because when I write it like this, it may appear that 3 is the first term because that's how this is written. But we have to really think about it in terms of just substituting the number in. What happens when I substitute the number in? Do I get 3 or do I get 3/2? It's whatever you get when you put this very first number in. Okay? All right. Let's move to telescoping series. So let's look at this. So it's a special kind of series. Sometimes they may be hard to identify which one is telescoping and which one is not. If it's written like this, if the first few terms are written out, it's usually pretty easy to tell. What it means is it's called this because it's the type of series that collapses to one or a couple of terms. And then if to a finite sum, then we can say it converges by the telescoping series test. Okay, so we're going to work through that. Well, first of all, let's look at this particular example. See how we have minus 1/2 plus 1/2? Those would cancel out. So we have minus 1/3 plus 1/3. And as this kept going, hopefully we could see that they would keep canceling. As far as we go, it collapses. And it leaves usually 1 or 2 constants, 1, 2, or 3 constants. This one leaves a 1. And then this piece over here, this end piece that we'll work on. So, this first example right here, it's not going to say use telescoping series. It's going to look like this, and you might think, gosh, I'm not sure what that is. If that ever occurs to you, one good thing to do is to write the first few terms. See if you can figure out what's going on. So let's write the first few terms. So I'm going to put a 1 in for my first term. And I'm going to get, 1/3 minus 1/5 plus, because we're summing, this is our summation right here. Let's see, we put a 2 in. We get 1/5 minus 1/7 plus, we put a 3 in, we get 1/7 minus 3, what is that, 1/9 plus ... and hopefully we can tell with the first few terms that it's telescoping. So notice how the negative 1/5 and the positive 1/5 go away, the negative 1/7 and the positive 1/7, and they're going to keep doing that as many terms as I write. So the way that this test works is we we figure this out. We figure out what terms are left over. In this case, it's a 1/3. So what I'm doing is I'm writing my S sub n term. I'm writing my partial sums term. So my partial sums, this poor little 1/3 guy, he's left behind, right? He's not going to get to cancel out with everybody else. So he's left. And then what I have to do is come up with an expression for the piece that is still to be subbed in. And normally it's just this piece right here. Not all the time, but normally it's just this piece. Because if you think about it, what it needs to do is it needs to generate these second ones. Whatever I put here needs to generate these numbers right here. And the thing that would generate this number would be, if I put a 1 in, I would get a 5. And what would generate this number is if I put a 2 in, I'd get a 7. And what would generate this, if I put a 3 in, I would get a 9. And see, that's exactly what this does, doesn't it? So this is what's left. And then what we do is we take the limit of that those partial sums. We take the limit going to infinity. Okay, and what do I get? So the 1/3 isn't touched by the limit. What happens to this term right here? It tends to 0. So I actually have a number, since I have an actual number as my limit, that this particular telescoping series converges. So we would say, therefore, it converges by the telescoping series test. So now we have 2 tests on our belt. We have geometric series test and telescoping series test. Now I need to point out, sometimes these telescoping series are hard to determine. So if you'd make yourself a note somewhere, this is a kind that I don't have on here to do an example of, but you certainly may come across it. So it could look like this. So where n equals 1 to infinity of 1 over n times n plus 1. This one is kind of disguised. It doesn't look like it would be telescoping. What we would actually have to do to this one is use partial fractions. We would have to use partial fractions to write it so it looks like this. You know, we'd have to use partial fractions to expand it, and then we would use the telescoping test to prove that it converges. So I'm just showing you this just so you're aware that they can get more complicated than the one that I have shown you. It is possible that it perhaps looks like this, and you have to use partial fractions. Okay? Let's look at our third test. Alrighty. The third one that we're going to look at today is called the nth term test for divergence. Now, it's really important, and I have it highlighted. It's really important. Okay, really important. This is a test that is only used for divergence. If this doesn't work, it doesn't mean that the series converges. It is only, out of the 10 tests that we look at, it's the rare one. This one tests for divergence. It doesn't test for convergence. It's a handy little test to have, because if we can use this test, we can, eliminate some of them just by using this quick little test. Let's talk about what it is. So if I take the limit, now this is our nth term. This is the little formula that generates all of our terms. That's why it's called the nth term test for divergence. It's using the nth term. If I take the limit as n goes to infinity of the nth term and I don't get 0, then the series diverges. Now we think, wow, isn't that so cool? I could get anything, 2, a half, infinity, anything, and we can say it diverges. So you would think that that would cover like a bunch of stuff. Well, a little. So many of them actually tend to 0. So I always, so on your paper, when you have a quiz or a test or whatever, you're just going to have a list of all these problems. And as you look through them, it's be a good idea to kind of think through the limit. You don't necessarily need to write it out unless you're going to use this test, but think through the limit and see, if I took the limit of this, is it going to be something other than 0? If it is, it's like, great, let's do this test and write the test out. Okay, so let's do that. Let's work with it. If it doesn't work, it doesn't mean that you're done. It doesn't mean, oh, sorry, I can't do anything else. What that means is basically the test doesn't tell us anything if it equals 0, and you're going to have to pick another one. You're going to have to try another one. All right, so let's look at these. This first one, hopefully this is my nth term, a sub n. So the limit as n goes to infinity of 2n plus 3 over 3n minus 5. So I take that to infinity, and hopefully we are at the point where we can do that in our head. We talked about this yesterday. And this is going to be 2/3. So this does not equal 0. Therefore, it diverges by the nth term test. I'm fine if you just write nth term test. You don't need to write the nth term test for divergence. Okay, that's pretty nice. That's pretty nice. Let's look at the next one. Let's work on this test again. So the limit. Now, I do want you to notice, because I keep getting asked, what work do I need to show? I keep getting asked that. This is the work that you would need to show right here. I'm showing you the work that you need to show. You would need to show the limit, what you're taking the limit of, the answer to the limit. It's not 0. And you say diverges by the nth term test. You'd be done. Okay, that's the work that you would be expected to show if you use this test, and it works. So the limit as n goes to infinity of n factorial over 2n factorial plus 1. Our goal is always to get rid of the factorials. Actually, what I'm going to do is I'm going to do a version of this test that we used to do on this one, just so I can show you what's going on. I would multiply by 1 over n factorial over 1 over n factorial. That's like multiplying by 1. So limit n goes to infinity. I get 1 over 2 plus 1 over n factorial. All right. What happens to this little piece right here? It tends to 0. So I'm left with 1/2. 1/2 is not 0. So, therefore, it diverges by the nth term test. Okay? Last one. So limit as n goes to infinity of 3 to the n minus 2 over 3 to the n. We would use this similar technique. If some of you want to just do that part in your head, please do so. Or, actually, I can, since I just have one term in the denominator, I could split this into 2 fractions. That might even be easier. So the limit as n goes to infinity, so this fraction would be 1 minus 2 over 3 to the n. This piece tends to 0, and so I'm left with 1, which is not 0. Therefore, it diverges by the nth term test. All right. And that is our lesson.